Good morning, everybody. My name is Mia Kühlewind. You want to introduce yourself, Dave? It's okay.
Yeah, and I'm Dave Blanco.
Welcome to the MAPRG session at IETF in Bangkok. We have a bunch of nice talks, but before we start, we go through the usual things that are important to note. This is an IRTF session, but the IRTF session also has a note well. This concerns IPR, so please be aware. I think you should have seen this by now, hopefully. This session is being recorded. Please be aware of this if you speak up. Also, please sign into the Meet Echo. If you want to speak up, you can use the Meet Echo queue. We have a privacy and code of conduct, privacy policy and code of conduct. We would like to have this as a nice session, so let's all behave appropriately, ask questions, have some good discussions. Looking forward to that. The IETF is not the IRTF. We're not doing standards in this group. In this group particularly, we're mostly looking at research papers and measurement results. This slide you find in the slide set for all the important information. It gives you the information about the charter of the group, so you know what this is about. We have a mailing list. Please subscribe to the mailing list because that's also where we send our call for contributions if you ever want to give a presentation here. You find the slides and the Meet Echo link here. Again, please sign into the Meet Echo. This is important for housekeeping, so we get a large enough room, but you also need the Meet Echo to join the queue in the room. Yes, there is an on-site tool you can use in the room. As I said, this is for joining the queue. For remote participants, we really recommend to use some headphones. Please keep your video and audio off when you're not talking, but you're welcome to turn your video on when you're presenting and talking. Okay, that's our agenda today. Usually we actually don't do an agenda bash, but if anybody wants to, we can. We have a bunch of nice presentations. First, Dave will give a quick heads up about the hackathon activity he was running. And then we have a bunch of papers from PEM actually, but we also, the first talk will be a paper that has been accepted but not yet published, so we get a preview of that one, which is really nice.
Thanks, Miria. And one of the things we said, we're presenting some existing work here, which is one of the things we bring to the IETF environment, but the other thing we do is active measurements. We haven't done that for a while, but this time we did resume it. So there was a MAPRG table at the hackathon, and I brought this piece of equipment provided by Internet2 called the IPv6 test pod. We have an open call for participants. We did for this last weekend, and we will for the next time. I will intend to be in Madrid and have this gear there. You can find details about it on the hackathon page that's shown as a sort of an eye chart here, but we had a pretty nice time there with a number of people visiting. But the idea is that this device can present 5 different kinds, or does present 5 different kinds of IPv6 transition networks, both wireless LANs and wired LANs to you, so that you can just immediately pick between them and test application support and operating system support for compatibility with these. Next slide, please. And I created, again, an eye chart, but I created a spreadsheet showing how I tested different browsers with different version numbers and a various number of apps on my Android phone with this, and used the IPv4 application to measure success for some of them. And then when that wasn't an appropriate way to test, we use another way. Just in the short time we did this over those 2 days, we got comments like, this little box you have is pretty useful. So you can just come up and conveniently change at a moment's notice between different kinds of transition technologies, including IPv6 mostly, Pref6.4, DNS6.4, IPv6 only. Next slide. To give you a small glimpse of what kinds of things I saw, I tested some applications that I need to use in my work environment, like Oracle's NetSuite. And this thing can tell you, for instance, when you're using a Pref6.4 prefix, when it's v4 only. Next slide. And then this gentleman, the thinker, stopped by and tested out some, this is Tommy Pauly, who's involved in the Happy Working Group and the Happy Eyeballs v3. And Tommy got some testing done and taught me a little bit about how the Apple Happy Eyeballs works on the various wireless LANs. So to wrap this portion up, Eric and Tim from the Happy Working Group, which met last evening, asked us to put out a call for measurement results having to do with Happy Eyeballs implementations, and then ongoing participation with Happy to test what's going on. So MAPRG will team up with Happy, and and we're calling for you to both be a champion of the hackathon event with me. You guys can borrow this piece of equipment. It's the MAPRGs. I asked for it from Internet 2 for the IETF and MAPRG, and we can continue that work there. So that's what I wanted to share. After the session, you're welcome to come up and ask me about it or take a look at this device. So next up, we have Weitong, and I think we're starting with the easternmost time zone and going to the westernmost time zone. And Weitong will share the slides and then pass control to you.
Thanks. I just saw the slides. It works perfectly. So let's just start and to save some time. So today we are talking about our recent work about measuring collateral damage in RPKI-RV. This work has been was being done by Weitong, Yuze, and TJ from Virginia Tech. So let's first talk about the it's a little bit delay. So let's first talk about the BGP and RPKI. So that we all know that the BGP is designed like more than 20 years ago, and there's lack of a security mechanism to protect them from being hijacked. So in recent years, the IETF are working into a new protocol called RPKI, which use the public key infrastructure to secure the BGP from being hijacked. Currently, more than 50% of the IP space are already protected with the RPKI. So how RPKI works is that because it's a public key infrastructure, so we have a certificate. So the resource owner, like the guy who owns an IP prefix, will create a certificate called root origin authentications, which is the certificate of the IP prefix and AS number that are allowed to announce that. These certificates are signed by the IRs and are stored in public repositories. So then we have the RV, root origin validation, which is deployed in the routers on the internet. So if the RV routers saw that there's two guys announce the same prefix from different AS numbers, and he wants to know who is the hijacker and who is the legitimate owners. So what the RV router will do is that he will download all the certificates with validations and just check the AS numbers in the raw certificate and against the AS numbers in the origin of the BGP. So if the AS numbers in the ROAS and in the BGP announcement matched, which means that it's RPKI valid, then it's all good. So if the AS number doesn't match with the ROAS and the BGP origin, then it means that it's RPKI invalid and it might be a BGP hijack, and the RV routers need to drop that. And then after the BGP announcement being dropped, the traffic will go to the legitimate owner of that prefix, so it's being protected from the hijack. But this question is that although there's a couple years from the ROV being deployed, it's still not many networks today on the internet are deployed fully ROV on all their networks. So ROV is still partially deployed. Around like 20 to 30% of the ISPs on internet today. So then it leaves a question. So because the goal of ROV is to protect one network from being hijacked. But if you are pairing with another non-ROV routers, then the things will go a little bit tricky. As you can see, the RV routers will still receive the RPKI valid and RPKI invalid BGP announcement. He will do the validation and find out one is hijacker and one is the legitimate owners. But the thing is that that's the nature of the BGP, that the one routers can only decide which next hop he wants to forward traffic instead of the whole path. So he has no choice but to forward traffic to the non-RV routers, which is his neighbor. And when the traffic goes to non-RV routers, because this guy is non-RV, he don't care anything about RPKI, and he will just forward the traffic maybe to the closest network or something like that, and the traffic may still go to the attackers. So this leaves the question that even when network deploy RV perfectly on their routers, they just deploy the reliability software, deploy the RTR, install a lot of stuff in their routers, making a extreme effort on securing their network. But if his peering or his upstream networks are non-RV routers, they still have a chance to be hijacked. So we call this the collateral damage in RV. So our RV-enabled network can still be hijacked with RPK invalid announcement if any hops in the past are non-RV. So RV is still far from fully deployment, so the collateral damage will be a long existing challenges. Then we know that the collateral damage exists, but the question for the measurement study is that how many networks are now suffering from the collateral damage, and how hard this collateral damage make to this network. So to measure that, firstly, to make the collateral damage happens, there need to be both RPI valid and invalid perfect. Because if there is only RPK invalid perfect, then once the RPK invalid perfect being dropped, there's no route and the traffic won't go to the next hop. But still, we first found out that mostly more than 80% of RPK invalid perfect have accompanied RPK valid perfect, which means that the collateral damage could happen for most of the RPK invalid perfect today we're seeing in the network. And below is the figure we measure for the old RPK invalid perfect from the BGP announcements we collected from the root. Then we design our experiment to measure how many RV networks are suffering from the collateral damage. So to measure that, we leverage the parent testbed, which allow us to announce both RPK valid and invalid announcements from multiple vantage points. Then we leverage RepLS, which is the measurement platform that allow us to run some pings from more than 3,000 ASs. So we first announced one single RPK invalid perfect from the parent testbed, and then we run ping from the 3,000 RepLS value point to our RPK invalid perfect. So if the RepLS nodes are resident in the RV networks, the RPK invalid perfect should be filtered out and the ping should not be successful. But if we're using our non-RV ASEs to run the ping, then the ping will go through. So then we focus on these RV networks, because you first need to deploy RV, then being a victim of the collateral damage. So we then also announced another RPK valid perfect, also from the parent testbed, but from different origin areas and different locations. So if the collateral damage happens, then which means that the ping from this RV network can still go through, but it will reach to another destinations. So, and if there's no cross damage, the ping traffic will go to the legitimate RPK valid announcer, and if there's cross damage, will go to the hijackers, which is also controlled by our parent testbed. So as for the result, from the 3,000 ASEs that RevLS measurement platform covers, firstly around 900 ASEs are protected by the RV if I only use the single RPK invalid perfect. And among these 900 ASEs, we found that more than 30% of them are able to reach the RPK invalid perfect after we announced the /23 RPK invalid perfect, which means that 30% of them are victim of the collateral damage. And also, we consider, because collateral damage usually happens in the nest hope, we also by checking into the ES relationship dataset, we found out for those ASs who are victim of the collateral damage, we found that most of them have non-RV nest hope, just as their neighbors. And no matter you have only single upstreams or you have multiple upstream, but only one now always it's always let you like more than 80% possibility to make you suffering from the cross damage and make the hijack happens. And also, if your upstreams or your peers are fully protected by RVs, which means that no matter you have 1 or 10 upstreams, they are all RV, then it's very little possibilities that you are being suffering from the collateral damage. But there's still be a possibility because the collateral damage can happen in any hopes of the path, which means that even your next one hope of the neighbors are all RV, the traffic go to next 2 hopes and it's still there's a possibility to suffer from the collateral damage. And then can we have more this challenge of this research is that we don't have many RPK invalid perfect, right? So what we are doing is that we also use in the wild RPK invalid perfect because we have like more than 7,000 RPK invalid perfect on the internet, and we want to use these perfect using as the measurement. So the challenge of using the perfect that we are not controlling is that if we only send a ping to these RPK valid and invalid perfect, we don't know where the ping goes to, right? Because the IP address is the same. So what we are going to do is that we need to use traceroute instead of ping to tell where our package eventually reach to, whether the invalid or valid BGP origin. To do that, we first check the BGP message and check the origin ASs and also the nest hope. For example, there's ASX and Y as the nest hope. And then we send our traceroute toward this RPK valid and invalid IP space, and we are just checking the last 2 hope of that traceroute result, and we see that this traffic is going to ASY, which means they're reaching to the RPK invalid origin. So by running this experiment, we see that 63% of them are reaching to at least one RPK invalid origin for all these RV ASEs, which this number is larger than our controlled experiment, which means that the collateral damage may still happen if we are considering more RPK invalid perfect. So then, in conclusion, firstly, most RPK invalid perfect have accomplished RPK invalid perfect, and the collateral damage is weakening the protection of RV for more than 63% of the ASEs who deploy RV themselves. So why this collateral damage happened is that the BGP still can have no choice to forward the traffic to the upstreams. But we deploy something like we let the router know, who is the non-RV routers and who is the RV routers by looking into the BGP announcement. And if one neighbor forward a BGP invalid announcement to me, then I will tell this guy is a not safe neighbor. So if this hijack happens, I need to forward my traffic to a safer neighbor instead of him. So we have proposed a new implementation of the RPKI, and we're presenting that part of mitigation in the Usenet security this fall. Thanks a lot, and if there's any questions.
Thank you, Weitong. So this was the paper that is accepted but not yet published. So thank you for presenting it here. And we actually have some time for questions. Go ahead, Matthias.
Hi, Matthias Welisch from TU Dresden. I'm a little bit confused about the wording here. Collateral damage. Which protocol introduced the damage? As far as I understand, the topic that you discuss here is due to the best path selection of BGP. So it's completely unrelated to RPKI.
So it is the RPKI. So because RPKI is based on the BGP, right? And due to the nature of the BGP, the one router have no control on the forwarding paths. So he has only control on the next neighbors. So
no. I mean, BGP is announcing the best path. So in your example, the leftmost AS or router is receiving exactly one path to this prefix.
Yeah.
So I still don't get why RPKI is a problem.
I see. So, if there's two different AS announcing that perfect, right? So we have two paths. So one path is the RPKI valid one, and one path is RPKI invalid one. So the job for the RPKI is to make sure that the traffic goes to the RPKI valid origin, right? But the thing is that if the traffic goes through non-ROV ASs, it will still go to the RPKI invalid origin.
Okay, not sure whether I get it. Okay, maybe offline. Thanks.
Thank you.
Wendy, do you want to ask a question?
No, sorry. I'm waiting on the
Yes,
brief.
we will call you up later. Thank you. Okay, any more questions? Then let's go to the next speaker. Do you want to bring up the slides? Thank you. So our next speaker is Fatis. This paper is about, this was published last week at PEM, so it's brand new. It's about L4S, and you should have, go to the top. No. If you can just enable your video and audio, yes, there you go. And we hand over slide control to you. Thank you.
All right, Fatish, you should have the slide control and you have 15 minutes.
Mm-hmm. Yeah. Hi, everyone. My name is Fatih Berkay Sarpkaya. I'm a PhD student in New York University. And today I will present our work, which is to adopt or not to adopt L4S compatible congestion control understanding performance in a partial L4S deployment. I would like to start with some brief L4S background first. L4S is low latency, low loss, scalable throughput. This architecture is designed to enable both high throughput and low latency through a combination of end-to-end congestion control and queue management. And this design also gained some industry traction, like Nokia, Apple, Ericsson, Cable Labs, Comcast, NVIDIA. All of these companies use this architecture in their trials, deployments, and their services. This architecture has three core mechanisms. Scalable congestion control and accurate explicit congestion notification are implemented on the endpoints, and dual queue, active queue management is implemented on the routers. I will explain these mechanisms very briefly on the following slides. But as can be seen, unlike the other low latency mechanisms, this system includes both endpoints and routers in the internet. Let's start with scalable congestion control. This mechanism is necessary to maintain very low queuing delay, and we can understand this by looking at this congestion window over time plots. In the first plot, you can see the Renault behavior without any ECN mechanism on the queue. Without ECN, it fills the buffer, keeps increasing congestion window up until the buffer size, so the latency is high. You can see this by looking at the blue dashed lines, and you can see the average queuing latency here. In the second case, let's say we implement ECN, like 20 millisecond ECN threshold. This time with ECN, it doesn't fill the buffer. It just goes until the ECN limit, so the latency is lower. You can see the average queuing latency also here. In the third one, let's say we want to implement very low ECN threshold, like 1 millisecond. This time, even if we get very low queuing delay, you can see the average queuing latency here. We observe underutilization because it decreases the congestion window too much when it sees ECN signal, and it needs some time to increase the congestion window. So because of this behavior, even if we observe low queuing latency, we have very low utilization. In the last one, this is the scalable congestion control, TCP-PRAG. This is the main congestion control to L4S. In this case, PRAG solve tool is much finer. That's why it can achieve high utilization, even with very low ECN limit. So PRAG can adjust its congestion window by using accurate ECN according to the congestion level in the network. So because of that, you can see the sawtooth difference between the other cases and the PRAG case. So we can have very low average queuing latency at the same time high utilization. This is the one key part of L4S, scalable congestion control. Because of this difference congestion window behavior, classic ones, the cubic or Renault, and the L4S flows do not coexist well in the same queue. We need to isolate them. Because of that, L4S proposed this two queue, double queue, dual queue, coupled dual queue mechanism, actually. L4S flows come to this bottleneck, and the other classic flows also come to this bottleneck, and they are classified according to their ECT code points in their IP header. So we differentiate, we isolate these L4S flows and the classic flows, and so that we can apply different ECN thresholds to these two queues, and we can couple these two queues to ensure that we fairly these two queues fairly shared fairly between the two queues. Actually, we can share the benefit fairly. So this is another core mechanism of L4S. And as I explained, there are lots of mechanisms. Actually, scalable congestion control, accurate ECN at the endpoints, and L4S aware bottlenecks on the routers with multiple queues or dual queue with shallow ECN marking. We have some core mechanisms of L4S. However, as traffic traverses the internet, it encounters network segments with varying levels of L4S support. Some segments may fully implement all L4S components, while others may have partial or no support. As a result, L4S deployment will be incremental. And in the early stages, L4S flows will coexist with other flows types at bottlenecks that may or may not be L4S compatible. With this motivation, our work is from the sender's perspective. The question is, as a sender, should I use L4S or not? And for this question, we need to consider that this sender usually must make the decision without full knowledge of whether the bottleneck queue it encounters will be L4S compatible or whether other flows sharing the bottleneck will also be L4S flows or classic flows. For instance, this bottleneck could be FIFO, FQ, Pi, Codel. It may support ECN or may not support ECN. It may be also dual Pi too. This is what the L4S bottleneck. Also, the other shared flows could be cubic, Renault, BBR, PRAG, the other flows. They may support ECN or may not support ECN, but this sender usually is not aware of these things. It's not aware of the bottleneck type and competing flows. So with the evaluation of different network scenarios, we would like to show if a sender uses L4S congestion control, would it cause any problems in the internet, or would the sender be able to get the low latency benefit of L4S? And by understanding this, we would like to show the benefit of L4S and point out some possible problems. Accordingly, we designed some experiments on Fabric testbed. We have two senders and two receivers. One sender is an L4S sender. It sends L4S flows for 60 seconds, and another sender is for classic flows. It sends 60 seconds flows. And our network condition is 10 millisecond base RTT and 100 megabit per second bottleneck link capacity. We believe that this is the representative of an access thing, and it could be the bottleneck in the real network. And we evaluate different kind of bottleneck types and different kind of classic flow types and L4S flow types, and I will explain them in the following slides. Let's start with single queue types on the bottleneck. We consider all these different type of queues, but these two marked with a green star are known to be commonly deployed on the real internet queues, FIFO and drop-based Pi. Other single queue is with ECM ones here are known to be rare or not exist, but we are interested in kind of breaking down the different contributors to alpha performance. I can attribute this classification to personal communication with Greg White from Cable Labs and also IETF draft document about operational guidance about single queue classic ECM bottlenecks in alpha deployments. You can see the references also here. These were all the single queue types. We also have multiple queue types, and this star again mentions that it's prevalent in the internet. FQ-Codel is known to be prevalent in the internet. We also put this star to dual Pi 2 because it's not prevalent here, but it is getting deployed as an enabler of alpha-OS. Also, we have alpha-OS aware FQ-Codel. Again, it's not prevalent, but perhaps prevalent in the future because of its alpha-OS support. In this type of FQ-Codel, this type of queue can put different ECN thresholds to alpha-OS flows. It's aware of the alpha-OS flows actually, so it can behave differently to the alpha-OS flow. So we also evaluate these multiple queue types. We have also different alpha-OS congestion controls. I already mentioned about PRAG, which is loss-based, the main alpha-OS congestion control. It supports accurate ECN. We have also alpha-OS compatible BBR version 2 in the Linux PRAG kernel. This is available. BBR version 2, the sender can mark BBR version 2 as an alpha-OS flow, and it supports accurate ECN and it's trace-based flow. And also in the dual Pi 2, it goes to the low latency queue if you use this type of flow in the sender. And we have some classic flows as a non-alpha-OS congestion controls. Cubic is the most common one, which is loss-based, and it supports classic ECN. We also evaluated BBR version 1, version 2, and version 3. Version 1 doesn't support ECN. The other ones support ECN, and they are all rate-based algorithms. And as an illustration for the methodology, I just put this heat map. I want to use this kind of heat map in the results section, but to just show our methodology, I put that. In here, we see the competition of PRAG versus Cubic. And you can see on the y-axis different bottleneck types, FIFO, Pi, Codel. And on the x-axis, you can see different buffer sizes. And here we are evaluating the throughput share of PRAG and Cubic. The color codes means that if it's red, it means that PRAG dominating Cubic. Actually, you can see that it is 100 megabit per second bottleneck. And you can see the numbers in terms of megabit per second. If it is red, PRAG is dominating Cubic. If it is dark blue, for instance, Cubic dominates PRAG. We do this analysis in the paper, and also we did that for throughput share and also for the queuing latency to understand the coexistence in different bottleneck types and in different scenarios with ECN or without ECN, etc. And I would like to show you some key results one by one. First one is about single queue with ECN support. It's a well-known results actually, as we validate this with our experiments also. In this case, alpha-OS flows dominate. Single qubit classic ECN, in our measurements, alpha-OS flow captures 75 to 90% of capacity and leaves classic flow with as little as 10%. The reason of this, because of these different reactions of alpha-OS flows and the non-alpha-OS flows. Actually, you can see the congestion window difference, as I already explained. Because of that, because of this difference, PRAG dominates the Reno, actually, the classic one. And we are aware that there is no known deployment of this type of queue at scale in the internet. However, as mentioned in the IETF draft document also, there is some possibility that such deployments exist, and there is the possibility that they could be deployed, enabled in the future. Therefore, we want to validate this issue with our experiments. And since they could theoretically exist in the network, we did this measurement also for the research purposes. We want to validate this issue with our measurements also. Another key takeaway is about dual Pi 2. In our measurements, we observed that dual Pi 2 doesn't work well with BBR. In that case, BBR flows by default goes to the classic queue. And this dual queuing system is not designed for that type of flows, because BBR is not that responsive to the losses or drops or ECN markings. So because of that, alpha-OS flows gets less than 5 to 15% of capacity against all the BBR versions. We observed this in our measurements. And this finding is concerning because of the increasing prevalence of the BBR on the internet. And this is a finding that applies to one of the queues that we believe are worthy of special attention. So because of that, we put this green star here, again, similar to the table. In the table, we have seen that. The other finding is about fair queuing. Not surprisingly, fair queuing allows safe coexistence. With a fair queue that enforces flow isolation, any variety of alpha congestion control can coexist with any variety of classic congestion control. In our measurements, we confirmed that. And alpha and classic flows share the capacity fairly. One side note is about latency. In fair queuing, normally by default, fair queue doesn't behave alpha flow and non-alpha flow differently, but alpha aware FQ codel can do that. With alpha aware FQ codel, it puts different shallow threshold for alpha flows. So because of that, it also supports ultra low latency for alpha flows. So as I mentioned, it's not prevalent for now, but it could be prevalent because of this behavior, this feature of this queue type. So because of that, we put green star here. And one last note, key takeaway is about latency. Low latency requires full alpha support because we can realize the ultra low latency benefit of alpha only when all of the ingredients are in place, like scalable. You need to have at the center scalable congestion control, and you need to have accurate DCM on the both endpoints, and you need to have alpha aware bottleneck on the routers. If you can provide these things, alpha flows can achieve sub-millisecond queuing latency. We confirm this also in our measurements. And as a very high-level key conclusion, early results from controlled deployments have been promising. You have seen some controlled deployments also, probably. But given that the sender of an alpha flow cannot be sure what type of queue is at the bottleneck router or what other flows will share it, safe coexistence across the internet cannot be guaranteed right now because of the problems I already mentioned. You cannot guarantee that as a sender, I don't know the bottleneck type, I don't know what type of other flows share that bottleneck. I cannot guarantee that if I use alpha there won't be any problem, or I cannot guarantee that I will get the low latency benefit of this service. So alpha flow using congestion control may be start by or starve other flows at a shared bottleneck. So this is our very high-level conclusion about this study. And that's all from me today. Thank you very much. You can reach our experimental artifacts by using the GitHub link. Also, you can scan the QR code. Yeah, thank you very much. Yeah.
Thank you. And we have Martin in the queue.
Martin Duke, Google and L4S enthusiast. Thanks for the presentation. Always like to see data about how this is doing in the internet. Can you go back to slide 17, please?
Sure. Here.
Yes. I'm confused about this. Are you putting? So there are two queues in this, right? There's a low latency queue and an okay, great. So is your implementation of BBR marking itself ECT1 to get into the queue without any further?
In this implement, by default, it goes to the classic queue. It's ECT0.
Yes.
So it goes to classic queue in this implementation. Yeah.
Okay. And that was, so in the other queue was still punishing the performance of the L4S flow?
The other queue is for alpha flows, and it gets the very low throughput compared to the BBR. Actually, BBR dominates the alpha flow, but the latency is still fine, but the throughput share is not fair. I mean.
Okay. So, right. So the L4S flow is getting the latency it expects, but the throughput is lower because.
Yes.
Got it. Okay.
That's true.
All right, thank you. That's clear.
Yeah.
So, but this is specifically about dual pi square, right? This is the case where this happens.
Yeah, BBR have some problems also in some cases in single queue is bottlenecks. But here we have seen some cases in single queue, it's not that problematic, but in dual pi 2, we put that and BBR starts to get more dominance. I believe that it's because of the coupling mechanism of these two queues, and we measured that also. This classic queue produced some probabilities of marking probabilities, and because of this coupling mechanism, this high probability goes to the low latency queue also and cause problems for alpha also. I believe that this is a coupling design. I believe that BBR is not appropriate for classic queue because of that. Yeah.
Okay. Yeah. So we're just working on BBR in another working group, so we should look into that, I guess. Stuart.
Stuart Cheshire, Apple L4S enthusiast. Thanks for doing this work. You highlighted some issues, and one of your headline points was the internet is not ready for L4S. do you have recommendations? Because it's interesting to point out problems, but it'd be really helpful to point out solutions as well.
You're right. Actually, yeah, as a solution, I mentioned some two main problems. One is about single queue ECN, but it's known that it's not prevalent in the internet, so maybe it's not that big problem. Another thing about dual PI2 with BBR. Currently, I am actually working on that, something maybe better for BBR coexistence in dual PI2. I don't have any specific solution, but the solution could be some recommendation is without having compromisation with some other network providers, you cannot use L4S directly without knowing your internet. I mean, without knowing what type of bottleneck on your network path or what type of network on your path, you shouldn't use L4S because it causes some problems. So just one recommendation is this, but direct solution could be some another, maybe queue design or something for BBR coexistence or some other things could be. I don't have some very specific solution, but some recommendation maybe.
Yeah, and one very quick comment. I know the queue's closed, so I'll be quick. On slide 8, we don't need to go back to it, but you had a diagram of servers on the right that have scalable congestion control, and the end hosts on the left, you didn't say very much about.
Yeah, we are sending data from servers to end hosts, and on the receiver side, you don't need scalable congestion control.
Okay, so that was exactly my comment, which is, I would argue it is equally important on the end hosts on the left. And I'll give one example of what Lorenzo is saying more important. So it is very common with many technologies like cable modems that the downstream is much higher than the upstream. And my service right now is gigabit down and 35 megabits up, which is highly asymmetric. And the buffer bloat problems I suffer is when I'm uploading a video to Instagram or something and it chokes my network. At gigabit speeds, the downloads are pretty fast, and even if they do cause buffer bloat, they don't last very long. But I mean, I don't do Instagram, that's a bad example. When I'm filing a bug report and uploading diagnostic files, it can spend 5 minutes of saturating my home internet connection in the upstream direction. So to Lorenzo's point, scalable congestion control on the end hosts is arguably more important.
Yeah, thank you very much for your comment.
Yeah, if the people in the queue could be quick, that would be good.
Greg White, Cable Labs, and thank you also for doing this work. And I think it's an interesting angle to study the choices that an application developer has around congestion control. So you labeled the problem statement as, should I use L4S? And I guess the question in my mind is, what was the alternative that you're comparing against? So would an application, is there a different congestion control that would give a better result in every bottleneck scenario? So I think this is a complex problem, right? The internet is a big space, and lots of different bottleneck link types out there. Maybe I think labeling it as L4S is not a good choice, or not ready, is maybe overstating it a bit. And then particularly the final conclusion slide, which in bright or big red letters says L4S is not internet safe. You're really comparing the performance of one implementation of a congestion control, the Linux TCP prog, against a few others. There are already multiple L4S congestion control implementations out there with slightly different behaviors. For example, the Linux version falls back to Reno in the case of packet loss. Some of the others fall back to cubic behavior or have other characteristics. So I think labeling this as, in red letters, L4S is not internet safe, is really overstating it. So thanks.
Thank you very much for your comment. Thank you.
Ingemar, yeah, go ahead.
Helena, what's just one very short one. L4S capable 5G that implements what you refer to as a fair queuing, because you said put traffic in different data radio bearers. So you have a fairness between users and fairness between flows for the same user. So that is for I also would a bit against this. L4S is not safe yet, because I mean for a very big what you call bottleneck or choke point on the internet of 5G access. I can say that that is L4S capable when it gets implemented. So, thanks.
Abhishek, yeah.
Abhishek from Meta. Can you go back to that slide, slide 17, I think it was, where you were comparing BBR with L4S?
I am not controlling. Okay, you can. Okay,
Well,
17.
My question is, yeah, so what was the, so there is a conditional priority scheduler at the end of the L4S dual
Yeah.
queue. Do you remember what the settings of that conditional probability scheduler were? Like,
It gives, yeah, it's a credit-based scheduler. I mean, it gives 10% of the credits to the L4S queue and 90% it's reverse actually. It gives some prior to the L4S queue, and when you serve classic queue, it increases the credits, and when you serve L4S queue, it decreases credits or reverse, kind of. Yeah, kind of this thing, a credit-based system, conditional priority scheduler actually. Yeah, but.
Do you think it was 10:1, 9:1 in favor of L4S or in favor of BBR for this?
Favor of L4S queue. Yes, favor of L4S queue.
So 9:1.
But I believe that because of very high probability of classic queue, it generates very high probability, marking probability for BBR flows, because BBR is not responsive to the losses, so it doesn't respond to this probability. So this high probability goes to the low latency queue also. Since L4S flow is responsive to this high probability of marking, so it is a problem between the BBR and L4S flow, I believe. So because of the coupling system, I believe it's a problem.
Okay, thank you.
Yeah, yes, thank you.
All right. Thanks, Vatish. Morty, I'm going to bring up your slides now, and you can put on your video.
Yep.
And you'll have 15 minutes.
Yep. Okay. Seems I can control where.
Go ahead.
Yep. Okay, so hello everyone. My name is Morty, and I'm now a graduate student in UCSD. And today I will present our paper, a deep dive into LEO satellite topology design parameters. And this is a joint work with my courses, Zahan, and my undergraduate advisors in Giza. And let's start. So nowadays, LEO constellations are rapidly growing. As the picture demo shown here, there are thousands of fast-moving LEO satellites at hundreds of kilometers altitude, providing internet service at all over the world. And compared to the terrestrial and the geo satellite network, LEO satellite has high global coverage, reasonable speed, lower latency, and also are cost-effective. Also, most importantly, LEO network supports a new advanced data transmission technology, the laser-based inter-satellite link. So what are the inter-satellite link? It is a fancy physical layer technology for transmitting data directly between satellites using the laser-based links. And here is an example image on the left, on the right. And without ISLs, LEO satellites can only interact with the ground stations using a band pipe topology. And this requires high-cost ground stations across a large number of locations on the Earth. But now with ISLs, we can directly forward the data from source through multi-hops across LEO satellites to the destination ground stations. And this enables LEO companies to build fewer ground stations on the Earth. And LEO constellations are moving towards more ISLs usage in the future. As far as I know, I think Starlink already uses ISLs in regions like Alaska. And imagine that in the future, all satellites could use ISLs to route data. Literally, it is a huge dynamic network. And our paper studied the performance of ISL-based topology on the various configuration parameters. Like the plot shown here, LEO constellations have some key parameters which forms the shape and determine the network performance. So altitude is the height of the satellites from the Earth's surface. And one constellation may have many shares. Each share has multiple orbits around the Earth with different phase shift. Each orbit typically has the same number of satellites evenly distributed. And the inclination is the angle between the orbit's plane and the equator, which determines the latitude one share can cover. And here's a parameter table for 3 proposed commercial constellations. Different constellations has different parameter shares. And on the right is a visualization for those shares. And you can see they have different density and coverage. We are curious about the logical guiding these parameter selections. What is the impact of these LEO share configuration parameters on the network performance? And to explore this, we choose the simulation-based method to measure the performance. of different LEO constellations with different parameters. The simulator we use called Hypatia, and the topology for ISL is plus grid, which is one satellite connect to 4 nearby satellites. And the user traffic is the end-to-end traffic of 100 ground stations choosing on Earth. And each simulation simulates 400 seconds movement of the constellations. And every second we compute the shortest path for all ground station pairs. Here's an example plot showing in time step the shortest path between the Hill and Brazilio through ISLs. And note that in this simulation, we do not account for any other real-world network factors like the throughput. This is a motivating example. We compare Starlink Share 1 with an example share we designed by ourselves, E1. We keep all settings the same, except for these 3 key parameters. And note that E1 has only half number of satnets of S1. And the latency performance is here. Y is the cumulative distribution, where X is the max round trip time between all 100 user endpoints during the 400-second simulation. The performance is better when the curve is more towards the left. And you can see that E1 performance is much better than S1, although it has only half number of satnets, which is a little bit counterintuitive because fewer satnets but have better latency performance. And this actually highlights the impact of parameter settings. So to investigate further, we designed 3 experiments to explore the magic of parameters. First, we simulate 3 major LEO mega constellations and analyze their network performance. The Starlink phase 1 has 5 shares, Kuiper has 3 shares, and Telesat has 2 shares. And next, in the synthetic configuration experiments, we conduct an ablation study varying the parameters like orbit count, satellite number per orbit, the inclination, one at a time to isolate their effects. And the last one is a progressive experiment to understand the relationship of user endpoints position and the inclination of the constellation. I will introduce more about this in detail later. And so for these experiments, we use 4 key metrics to assess the network latency and stability. First is the round trip time, which measures the time for data to travel between sender and the receiver. We track the max and the minimum RTT since LEO satellite's motion will change the network routing topology during time. We also track the difference between max RTT and the minimum RTT to show the latency fluctuation. And the second matrix is the path changes, which counts how often the shortest path shifts through ISLs. And more changes means more handover and less stability for the LEO network. And the third matrix is the geodesic slowdown, which is compare the actual satellite's pace to the ideal shortest path along the Earth's surface. So lower value means more efficient routing. The last one is the average hop count, which tracks the average number of hops data takes. Fewer hops means fewer handover and better stability. So let's dive into the experiment's results. First is the performance of different real-world commercial LEO constellation shares. I have chosen 2 key results to highlight here. The RTT variation and the path changes across Starlink share 1 to 5. And on the x-axis, we see the CDF across all endpoints pairs, and x-axis is the RTT variation and the number of path changes respectively. The key takeaways are, first, sparse shares lead to high RTT variation and frequent path changes, like Starlink share 3 and 5, which show a long tail in these 2 plots. The second one is denser shares with more satellites and better coverage generally have lower latency and more stable path. And third, not shown here, but shown in our paper. If you are interested, you can look the plot in our paper. Among commercial constellations, Kuiper share 2, Telesat share 2, and Starlink share 2 perform the best. And next is the results of synthetic configuration experiments to explore the mega constellation's parameter influence. So the first parameter is the number of satellite per orbit. There are some representative performance plots shown here. The left 2 plots show the max RTT for different number of satellites per orbit under the fixed orbits number, 20 and 33. The right 2 plots show geodesic slowdown for the same cases, and also the performance is better when the curve is more towards the left. Here are the key takeaways for the impact of number of satellites per orbit. The number of satellites per orbit is the key determinant of the network performance. As the number of SysNets per orbit increase, the latency and the geodesic slowdown in the network decreases. However, the diminution returns exists, and we found a critical threshold, actually 28 SysNets per orbit. Below this, performance drops significantly. And then we compare the number of orbits. We analyze the max RTT and the geodesic slowdown while fixing the number of SysNets per orbit, and we increasing the number of orbits. The left two plots show the max RTT of different orbits under fixed number of SysNets per orbit, 20 and 28. The right two plots show the geodesic slowdown for the same cases, and performance is better when the curve is more towards the left also. And we got three key takeaways. As the number of orbits increased, latency will generally decrease. And second one is performance drops significantly when both SysNets per orbit and orbits are below 20. You can actually see the second plot. Number of orbits seems matter less than number of SysNets per orbit, at least when number of SysNets per orbit more than 28. The small, you can see in the second plot, the small max RTT improvement. And how about the effect of the orbit inclination? We present 4 plots from left to right, and they are performance of max RTT, geodesic slowdown, RTT variation, and the number of paths changes for different inclination. However, as you can see, it's hard to determine whether higher inclination will improve the performance. That's why we designed the progressive experiments to dive deeper and uncover the hidden effects of inclination. To better understand the impact of inclination, I will first introduce the concept of geographic angle. It is the angle between equatorial plane and the plane that contains 3 points: the Earth center, user endpoints A, and user endpoints B. And our intuition is that the alignment between SysNets orbit inclination and the geographic angle of user endpoints affects the constellation's latency performance. If the orbit's inclination and the geographic angle between endpoints A and B are not aligned, the path is more likely to follow a zigzag pattern crossing multiple orbits. If the geographic angle is close to the inclination of the orbits, the shortest path is more likely to follow a single orbit for most of the distance. So to prove this, we categorize user endpoints traffic on the Earth into 9 groups based on their geographic angle, and we set the interval to 10 degrees. We evaluated the network performance on the different inclination constellations, and here's a visualization for each group. We connect each user endpoints pairs using the red line, and the red lines has different geographic angle. And here's the number distribution of those pairs. Most of the user endpoints traffic are within 30 and 70 degrees. And here's a selective results showing geodesic slowdown for 3 groups of user endpoints pairs on the different inclination constellations. The y-axis is the ECDF, and x-axis is the geodesic slowdown. The performance is better when the curve is more towards the left. And looking at this plot, you can see the blue line, which is the performance of 45-degree inclination constellations, gradually be worse for endpoints pairs that has higher geographic angle. Meanwhile, you can also see the green line, which is the performance of 65 inclination constellations, gradually be better for endpoints pairs that has a higher geographic angle. So it is easy to see that when the orbit's inclination aligns with the endpoint's geographic angle, the latency performance is better. The average hop count has the similar pattern. From left to right, you can see 3 groups of user endpoints pairs performance on the different inclination constellations. The y-axis is the number of average hop, and x-axis are the 4 different constellations inclination. Lower dot on the plot means better performance. And as the right cycle point out in the plot, when the inclination aligns with the endpoint's geographic angle, the performance is better. We also have a more detailed analysis and analyzed how the average number of hops change among the same endpoints pairs. As an example, we selected endpoints pairs within the 50 to 60 degree range and plotted their number of average hops by dividing them into different distance. From left to right, the inclination is increasing. Y-axis is the number of average hop counts, and x-axis is the endpoints pairs distance. So focusing on the city pairs between 10,000 to 12,000 kilometers, I already highlighted them in the red block. you can see how the color distribution shifts as the inclination increases. As the red arrow showed above, when the inclination matches the geographic angle of the user endpoints pairs, which should be 50 to 60 degrees in these plots, the number of average hop counts decreases. However, when the inclination increases beyond 55 degrees, start from the second plot, the same endpoints pairs routing path starts requiring more hops again. And this implies that when the orbit's inclination aligns with the endpoint's geographic angle, both the latency and average hop count performance will be better. So to conclude the summary of the findings, we can get these 4 conclusions. First, for the parameters number of orbits and number of sesnets per orbit, there exists thresholds below which performance drops significantly. And second, beyond the threshold, there is a marginal improvement in the performance as the sesnet's density increases. Third, alignment of the sesnet's orbit inclination and the user endpoint's geographic angle can improve the latency and hop counts performance. Fourth, considering both delay and link stability, Starlink Share 2, Kuiper Share 2, and Telesat 2 offer the best performance in each of 3 constellations respectively. So therefore, a suggestion for the newly planned LEO constellations: make sure the density of sesnets exists at the threshold and try to align in the inclination of the constellations with user endpoints geographic angle you want to serve. And for the future work, the future efforts could be put on studying alternative ISL's topologies beyond the plus grid structure or analyzing the performance of combining multi-share configurations. Also, we can consider add more real-world factors like congestion control during our simulation. And that's all. Thanks.
Perfect. Thank you, Gori. Come to the mic.
Gori Fairhurst, thank you for bringing this here. I think I understood earlier that you talked about metrics for less RTT variability as one of the metrics. Can you say just a word more about that? Because I think minimizing the disruption to the internet path may be more important perhaps than reducing the latency. So can you say just a word about that?
You mean explain more about the RTT fluctuation?
Yeah, yes. What can be done to reduce the fluctuation? Yes.
That's a good question. So what can be done to reduce the RTT fluctuation? I think one of the ways to deploy your LEO shells in a more aligned way as how your user ground station how your user endpoints distributed on the Earth. So for example, in our experiments, we found that actually if the inclination of the orbits are more aligned with the user distribution, they will have better RTT fluctuation performance. So I think that could be one of the possible way for the LEO companies. Yeah,
I think that'd be very interesting for the
and
IETF.
also add one more point. In the real world, actually, the SaaS companies usually try to improve their user performance by deploying more ground stations on the Earth. And our research is just all use the inter-SASNet links to forward the data. But in real world, they were just using several SASNets to forward the data till they hit ground stations on the Earth. Yep.
Thank you.
Hi, Gautam, satellite novice.
Hi, Gautam. I know you from UCSD.
Hi. I guess I think you briefly touched upon this in terms of like how satellite networks do it in practice, and I think one of the operational assumptions in the simulation was that it's always going to be bounced back to the satellites, and there is going to be a bent pipe always. But in practice, isn't it the case that once you hit the first ground station, you're going to use terrestrial routing to go to the home POP? So could you say a little bit about how the simulation differs from things done in practice? And is it possible to incorporate how things actually work, as in like the terrestrial routing as opposed to the bent pipe, assuming that it's always bent pipe, and also how Starlink does like the home POP? So have you thought a little bit about that? Thank you.
Yeah, that's actually a very good question. So Actually, when I do this work, after I done this work, I feel like the simulation, the way I simulate this question is not exactly how the real world SaaS company using the topology they used. Like just as I said before, for Starlink, for the place they don't have a ground stations, they just forward the data through the SaaS. Here they hit the closest ground stations, then they will forward the data through the terrestrial network directly. So I think that's one of the big difference for the simulation, for our simulation and the real world scenario, and it's also one of our limitation. But I think the good things about the simulation we have done is that for the future sense, if we have the enough ability to forward all the data on the sky, we definitely could get much lower latency than those terrestrial network backbone. So I think this would be the good side, the better side for simulation work than the real world application. Yep. Thank you.
Cool. Thanks so much for joining us, Morty. Shane, you can share your video and audio, and I'll bring your slides up.
Okay.
Yeah, we can hear you. And you got
Okay,
15 minutes. You're ready to go.
So how can I click like control the screen?
Oh, I gotta let you do that. All right. You should have control now.
Okay, yeah. Okay, I'll start. Yeah. Hello, everyone. My name is Xiao. I obtained my PhD at Duke University, and now I'm internet measurement researcher at Southern Eyes. Today, we are going to introduce our measurement research on the Anycast flipping. This is a joint research project with Akamai Technology. In this research, we want to figure out 3 questions. First, does Anycast flipping still exist? Second, besides DNS, which previously shows the Anycast flipping, does Anycast CDN also encounter the similar problem? And lastly, if Anycast CDN also be impacted by the Anycast flipping, how does it slow down the web browsing? IP Anycast is a routing mechanism that allows routers to announce the same IP prefix from multiple different locations. In this talk, we refer to each location where the prefix is announced as an Anycast site. For example, in this figure, I show 3 Anycast sites. Typically, each site has an on-site router and servers that receive client traffic. Suppose they all announce the same IP prefix. Based on BGP routing policy, different clients' traffic designated to the Anycast prefix may reach different Anycast sites. We refer to the site of clients that reach a site as the site's catchment. But for clients, it can also reach to multiple different Anycast sites, which is called Anycast flipping. Today, Anycast is used by many geo-replicated services, such as DNS root name servers, content distribution networks, and DDoS mitigation services. In this work, we focus on the prevalence and the impact of Anycast flipping. In this work, we first checked the Anycast flipping, again following Wei and Hedman's previous art, but extended the measurement with the date to current dates. We still depends on rep-s built-in DNS chaos query to verify. DNS chaos query is a special DNS query that retrieves the server's predefined identifier from the DNS instances. In terms of Anycast, it can be used to tell the location of the Anycast site. In this research, we processed and compiled a site ontology that is composed of 1,014 different chaos replies, and we are able to locate them by resolving their format. Most of them follows IETA and UN local code standard, but we also confirm with the latency and geographical information collected from the traceroute built-in measurements. After we have built the ontology, we evaluate the flipping by calculating the mean time between flips for each probe root pair for the first Monday of each half year. The 2 line plots below show the percentage of flipping probe for different routes. The left one shows Anycast flipping for all available probes at each day we collected the data, ranging from 8,900 to 12,700. To mitigate the change of red as probes, for example, one replicate probe could be deprecated. We also restrict the measurement to a subset of replicate probes that is still alive for all the first Monday of each half year. The red one shows Anika flipping for the probes that stay alive for all the 8 years, all 8 half years we collected. The number of probes ranging from 500 to 800 depends on different probes, different routes. It shows the similar trends. We could notice A route had a steep increase between the year of 2020 and 2021, increased from 2% to 9.5% in the end. We also evaluated the round-trip time slowdown brought by the Anika flipping. We plot the CDF of the actual time incurred by the Anika's flipping for flipping probes. For A route, we could see around 90% of the flipping probes only incur less than 12 millisecond actual latency. But for B route, 80% of the flipping probes suffer from actual latency that is larger than 120 milliseconds. For the long actual distance, we have an example, the RAP-S probe 6505, which is deployed in Singapore, consistently flipped between 2 C route sites, one deployed in Singapore, and the other one was deployed in Los Angeles, United States. The distance around the distance around them is 40,000 kilometers in terms of the Great Circle distance. According to our evaluation, Anika's flipping still have impact to the root name servers, but how about content providers? If it happens, will Anika flipping slow down the web browsing in terms of the different number of TCP sessions used in different protocols? In the second section, with the help of bright data, we managed to estimate how Anika flipping impact one major Anika CDN provider. We first host a dummy web page embedded with 15 different pixel images on that Anika CDN. And we utilize around 9,400 unique proxy nodes that came from 1,900 different ASs to request different resources on this web page from the CDN. We use the right flow chart to illustrate how we measure the Anika flipping for that Anika CDN. First, for one session, we send the request for 50 different resources to Bright Data's proxy controller, and the proxy controller will dispatch the request to available proxy nodes. Second, to ensure Bright Data's proxy controller dispatch all the requests for the same session to the same proxy node, we append a random session token to the request that belong to the same session. And the proxy controller will try to dispatch those requests to the same proxy node. Third, when the proxy node receives the request, it will try to resolve the host name and send out the request with different dedicated TCP sessions to available destination IPs. Due to the CDN host name was resolved to 2 different A records or IP addresses, and different Anika's IP could be deployed differently. We also instruct the proxy node to attach the destination IP in the response header of current request, along with the connect time, round trip time. To distinguish different Anika sites of that CDN, the CDN server also append a header following the IATA code that shows where the current request reached to. Therefore, for those around 9,000 unique proxy nodes, each one could reach to 2 different Anika's IPs. We aggregate all the requests from the consistent session by the same proxy node, destination Anika's IP pair. Thus, we could analyze the Anika flipping between the same resource and same source and same destination. In total, we got around 18,000 groups that have a unique proxy node and also destination Anika's IP, and 1/3 of them reach to multiple sites. For some groups, it can even reach to 9 different sites. In terms of the actual delay incurred by the Anycast flipping, we compare to the most site, which is the site had been visited most of the time during the same session to the same target IP. For the delta round trip time CDF, we could see, interestingly, 13% of the flipping groups actually have a negative actual delay, which means for those groups, it reached to a further site most of the time. But also we could notice that for 47.5% of the flipping groups, it have actual delay that is larger than 15 milliseconds. With the statistics collected from the CDN measurement, we also conduct the simulation to show the impact of actual delay brought by Anycast flipping to the web browsing. We extended Mahi, the web page recording and replay simulator to support HTTP2 replay and host-wise probabilistic delay injection. We start with our mock page that hosted on the CDN before. We set a 50% flipping chance with 15 millisecond additional round trip time. And for each parameter and protocol, we repeat the simulation for 100 rounds. And the right graph shows the actual time used to render the first content for pen and the whole page load time. You can see the whole page load time is segmented differently due to different number of TCP sessions used in different protocols. And the HTTP2 result shows a one-off impact due to only one TCP session is used to download all the resources. Therefore, if the single TCP session used in the download is delayed, the whole web page loading will be impacted. Besides the mock page, we also record 20 most popular websites from Tranquil list, and we also collect them from 3 different vantage points, 2 provided by Cloud Lab and 1 deployed in Duke. We save the latency from the vantage point to all the servers that send over the resource of those web pages at that time. And we identify those server IPs that belong to the CDN providers. For those CDN IPs, during our simulation, we will inject a 50 millisecond actual delay with a 50% chance. And for different protocol websites combination, different protocol websites and vantage points combination, we will repeat the simulation for 100 rounds with the flips and 100 rounds without the flips. From the simulation result, we found the median first content for pen slowdown is 81 milliseconds to 111 milliseconds for different vantage points that delivered by HTTP 1.1, and 77 to 109 milliseconds for different vantage points that delivered by the HTTP 2. The total page load time also follows the same trend. In summary, in this research, we first re-evaluate the Anycast flipping, which first observed in 2016, is still presented in 2024, and has grown more prevalent. Then, with the CDN measurement, we show Anycast flipping also impacts a small but significant number of CDN vantage points. The Anycast flipping can incur more than 50 millisecond actual delay. Lastly, with the simulation result, we show the impact of Anycast flipping on the web performance can be significant. And this is the end of my presentation. I'm happy to take any questions.
Thank you.
Thank you.
Yes, Wes is already walking to the mic, so I guess you want to join the mic queue, yeah. You can go first, Wes.
Thanks. Wes Herdiger, USCISI, and the operator of BRoot. So I appreciate the measurements. One of the questions that I have after reading your, so as you're aware, we know about it. John Heidemann, my colleague, you cited on your presentation.
Yeah.
What I'm always looking for in situations like this is, what do we do about it, right? How can we improve the internet? So we know that this is a problem. We know, especially for things like TCP, it matters less for UDP because the queries are going to get answered anywhere you send them. Do you have any recommendations? because from an operator point of view, I don't have control over why things are switching, right? It's always routing decisions that are made outside of my control.
Yeah. So that's actually a very good question. Yeah, because the anycast flipping can be caused by multiple factors. So one could be ECMP, the other one can be BGP multipass. And those are usually out of the scope of the original content provider's operator. So one improvement could be on the protocol side. So when we receive the BGP announcement, maybe we can do some label on that route, on that anycast route, so that anycast route can be stabilized on that part.
But the sender is the one that has the problem.
So you mean sender sent the announcement to multiple pairs?
So the sender of a UDP or TCP session is the one that is sending it to a different place because of a routing choice, either near them or in the middle between that and the server. That's why the server has no control.
Yeah. The sender reach out to multiple different sites. So on the sender side, on the sender side, it reached to multiple sites most of the time because it used the same hash value. So because the destination usually have a fixed IP address and a fixed port number, so it may be the source port could be a problem. So yeah, we could follow the same approach as Paris traceroute. So Paris traceroute also, the classical traceroute also have the problem that could be impacted by multipass because they have different hash value when you encounter some load balancer. But in the Paris traceroute, it manipulates the header in advance so that it can try to go to the fixed path as try its best to go to the fixed path.
All right, thank you very much. I encourage you to reach out to me. I think you're confusing a few concepts, and we should talk offline so we can get back to the program. Thank you.
Sure. Thank you.
Thank you, Lucas.
Hello. Thanks for presenting this work. I want to go and read in depth to make sure that I can understand stuff. As somebody that works at a CDN that uses Anycast, I can appreciate some of the things you're seeing. But again, I want to go into the details because I'm wondering, I've got a load of observations or questions that just spring to mind, what are these flips, from the data you're showing? These are something changed while or just before I was trying to establish a TCP session, and then it didn't flip while that session was open. But there can be issues that happen when things flip during a TCP session being active that can cause packets to land on the wrong place, and various issues come along, and reliability and other impacts on the kind of web page performance metrics you were showing as a result of needing to retry things. So that's certainly an interesting variant. Stemming from that, you have the idea of Quick and its ability to avoid packet or IP tuple-based routing with connection IDs. And there's a lot of interesting things that you could do as an operator that uses connection IDs for packet routing. And maybe that's an area you might consider looking into further, just as an extension. And then there was one more thing, and I've forgotten it. So if I remember, I'll post it in the chat. But yeah, thank you.
Yeah, thank you.
Perfect,
Thank you for all the information.
Check out the chat then. Okay, thank you for your talk. We go on to the next speaker, and Björn is here in person. Yes.
Yes, thank you for the introduction. My name is Björn. I'm with Domus, and I'll be talking about quality of outcome. Next slide, please. All right, quick agenda. First, what is quality of outcome? I assume not everyone has heard about it or seen the details, so I'll go through quickly on that. And then I'm presenting a simulation study with the intention of understanding engineering best practices for using quality outcome and the data collection that goes along with it. So next slide, please. All right. Our goal with the quality outcome stuff is to sort of bridge the gap between sort of abstract, or at least to end users, abstract network measurements like throughput and latency and things like that, and map those over to which applications will work well on this network, given the measurements that we can take of it. So trying to understand, like, will this network support gaming and video conferencing and other things like that, and make that available to the, or make that a score that the end user can see, like this network has like a video conferencing score of 100 or 90 or 10. And so to do that, we need to measure the network in a way that captures the features that we need to have. Then we need to know what the applications require. And then we need a way to compare those. And that's what quality outcome is proposing. So next slide, please. And I think you can click twice because I'm going to skip this one. All right. This slide summarizes what the metric is. This consists of 3 parts. There's the blue line, which is a CDF of measured network latency. And so that is something that we collect, or to compute the quality outcome score, you need to collect the latency distribution. The second part is these horizontal lines that are labeled 100 on one end and then 0 on the other end. And the idea with that is that is the way applications can express what they require in terms of latency. So these are, you will notice they are on the at different levels. So there's one here for the 50th percentile, one for the 90th, and one for the 99th percentile. The draft just specifies that you can have any list of combinations of percentiles and latency. And the leftmost ones, the ones labeled 100, is sort of the way an application can express that if the network is this good or better, then we don't care how much better it is. So it's sort of the point at which if the network improves beyond this, the app still won't work better in a sense. And then on the other side, on the right side, there's a 0, which is a way for applications to express that if the network gets worse than this, we don't care how much worse it is, because it's already so bad that the application is very unlikely to be able to function properly. And then the third element here is the quality outcome score, which in this case is 80.84, as labeled in the slide. And we compute that by just doing the linear interpolation of the point where the blue line crosses one of the black ones. And if it crosses more than one, then we just take the worst one. But in this case, it only crosses at the 99th percentile, and we get a score of 80. And of course, this might seem like simple enough, but if you go and try to implement this, you will quickly run into like, how do I collect the latency? How do I measure it? How often do I need to sample? Stuff like that, and that's what the study is about. So next slide, please. First, I want to mention that all the code for doing these experiments is available on GitHub. You will also find a PDF report with a description of the work and all of the results. So if you want to run your own version of this, it should be possible to get that up and running, I hope. And if it's too poorly documented, just send me an email. The goal of the study is to document how quality outcome is affected by these different engineering decisions, such as sampling rate, sampling accuracy, which is a side effect of the method that you use, and also the details of the application requirements, and it's quite or sort of related to the sampling rate, or the combination of sampling rate and time window that you look at determines the number of samples that you get in your distribution, right? I won't go into the application requirement results in this talk, just in the interest of time, but those are in the report as well. So if you're curious about that, it's available. Next slide, please. Okay. First, I wanted to show this, which is not really from the simulation, but it's, I think, a useful fact to have in mind when reviewing the results, which is this general property of fat-tailed distributions, that if you sample them with or if you collect just a small sample from a fat-tailed distribution, and then use that small sample to try to estimate something like the 99th percentile of that distribution, you're likely to underestimate the 99th percentile. And it's simply an effect of the outliers being rare, so you're unlikely to see them in your sample. So it's sort of I find this a bit fun, because if you have a small sample size, the average of your estimates is accurate, but each sample is likely to underestimate. So yeah, for this example, if you go to 1,000 samples, the estimate is very good, but if you have only 10 or 100, the variance is quite large on that estimate. Okay, next slide, please. This is a very high-level view of the simulation. It's a simple FIFO queue with an arrival process, or a set of arrival processes that feed packets into the queue. And then we have a DQ process, which is basically the simulated link, which takes one packet out of the queue every so and so often based on the link parameters, basically, that you set up. So for the Wi-Fi simulations, for instance, I've used measurement data from an actual Wi-Fi link to extract the pattern of TX ops that you get, and use that to dequeue packets from the queue. Okay, next slide, please. Okay, so these are the Wi-Fi results. There's a lot of data on this slide, but only really two concepts. So on the left side, we have different traces, different time series traces of the queuing delay in the simulation. And these are all run with the same parameters. So it's like the difference between these are just random seed, basically. And then on the right side, we see the estimates of the quality of outcome score based on, or as a function of, sampling rate. So what I've done is basically first generate a sort of high fidelity latency time series, and then subsample it at different rates and then estimate the quality outcome score with the subsampled sample set, and then done that a bunch of different times so that I get a distribution of the quality of outcome scores for each subsampling frequency, and then that's the bar or the box plots on the right side here. So the lowest sampling rate is one sample every 20 seconds. The highest sampling rate is one sample every 10 milliseconds, and then there's a range. So as you can see, as expected, if we have a very low sample rate, you get few samples, and you're likely to not see the outliers, which means that your quality outcome score is higher than you expect, because we don't see the problem. Like, there might be a problem in the time series, but you're unlikely to observe it. So you're likely to say this link is working well, when it's in fact might not be working as well as you needed to. So yeah, so this is for the Wi-Fi case. Next slide, please. This is for a different case where we basically simulate a network where like some misconfiguration or something is causing random service outages. So we have basically a small chance of spending 1 full second to extract the packet. And That happens just at random, so that's why these traces are different. And so to me, the interesting part about these results is that to notice this problem, you have to sample at a much higher frequency than you would for the Wi-Fi. Like the Wi-Fi is sort of, it's unstable, like the latency fluctuates a lot, but it's fluctuating sort of all of the time. So you're likely to see it even with a comparably smaller or less frequent sampling rate than what you need to see this problem. So basically, this is a much more difficult problem to notice, is the conclusion. Right, next slide, please. So yeah, I just wanted to remind you about this property. I think all of these, the results basically stem from this feature. And it's something to keep in mind when looking for network problems that aren't there all the time. And it's easy to sort of trick oneself into thinking that you have a good monitoring system that it will catch all the issues, but it might not if it's if the problem is sort of yeah, intermittent enough. Next slide, please. Okay, so just to conclude, when calculating a quality of outcome score or even just measuring latency in general, it's important to choose the correct sampling parameters. And what correct means depends on your use case. It basically depends on what kind of problem you're looking to detect. Is it something that is there most of the time, or is it a very intermittent thing? It also matters what the time horizon you care about is, because that determines the sort of interaction between sampling rate and sample size. And then, of course, like how accurate the scores need to be also plays into it. If you're okay with some variability, then maybe you can sample less often. And then to sum up, we've presented some simulated data here and open source the tool, and hope to help implementers make the right decisions, because now if they want to learn, like what rate do I need to use, how accurate does my samples need to be and stuff like that, they can go look at these simulations and at least have a reference point for, like, if the problem kind of looks like this, then these parameters are either very, like, will give me very accurate results, or at least, yeah, have some estimate of the variability to expect. So yeah, with that, thank you very much for your attention, and I'm happy to take questions.
Yeah, perfect. Thank you for doing the work.
If no one else has one, I have a quick question. Can I jump back to your slide 5? I guess I can because I have control. I didn't quite. I think I missed the thing about when you're specifying the 0 and 100. Am I an application writer that is deciding the bounds of what I'm willing to accept, or how does that part of this methodology work?
Yeah, that's a good question. So the way, like, ideally, I would like to work with the application providers to run tests on this with, like, simulated network conditions and learn what the application, like, how much latency and variability do you need to add before the application starts to have, like, problems or the artifacts that the users are likely to notice, things like that. But in practice, what we've done is to run those tests without the sort of without in-application measurements, if you like. So we've just, like, done like spin up a video conference, run some various emulated network conditions, and then see, like, where does it start to break, and then we use those requirements for now.
Thanks. We got Marcus in the queue. Let's switch to him.
Hi, Marcus Hiller Eriksson, and IPPM chair. I would just like to make some shameless promotion that this work is actually being specified in the IPPM working group. It is a pretty mature document, but we would like to get more people engaged in this work, because in IPPM we have a lot of experts on operations and management and metrics and so on. And as Björn points out, it would be really useful to get feedback from people running applications to see whether this way of measuring performance is useful. So we have this work, and we have some other work going on metrics around responsiveness under working conditions and so on, that are trying to achieve similar things, trying to define useful metrics and methods for defining application performance over various networks. So if you think that this is interesting, please engage in the IPPM working group.
Yeah, thank you, Marcus.
Yeah, okay, so download the code, talk to Björn, bring it to the mailing list, bring it back here, bring it to IPPM. Ah, sorry. Oh, Lucas, go ahead.
Yeah, just a quick one. Marcus's kind of comment then made me wonder how much outreach is going on into the application areas, such as like the W3C. There's recently been a community group called the RUM Community Group for Real User Monitoring that might be interested in seeing some of your work beyond. And I don't know if that's come up before, but if not, maybe I could put you in touch with those folks.
Yeah, so IPPM, we have not done much outreach like that, and I think that would be a very interesting thing to talk about. We have a couple of documents there that probably would benefit from that kind of feedback or discussions. So yeah, let's talk about that.
Yeah, thank you. I'm not sure I caught what you said, Lucas, but I'll send you an email and ask. Thank you.
Oh, Lucas, if you can send the right groups to our mailing list, then we can reach out to their mailing lists.
Sure.
All right, so we have Mahmoud up last. Mahmoud, can you turn on your video and audio? And we got your slides up, and once you do, okay, you got it. I'll pass control to you. We've got 16 minutes left in the session, so you'll take us through the end. So you're ready to go.
All right, thank you. Hello, everyone. My name is Mahmoud Ataya, a master's student at King Abdullah University of Science and Technology, otherwise known as KAUST in Saudi Arabia. And the topic of my talk is network mailboxes and their impact on HTTP conformance. This was a paper that was submitted and presented at PAM and is a joint effort by Ilyas bin Habour, myself, and Professor Marc Dacier. We also had the honor of receiving great comments on our paper by one of the authors of some of the RFCs mentioned in our paper, Mark Nottingham, and so we will also be addressing his comments throughout the talk. And so HTTP is an extremely popular communication protocol between web browsers and web servers, so popular that Cloudflare reported that in 2023, they saw 50 million HTTP S requests happening per second. And so what a connection usually looks like is the client sends a request packet with a request line, some headers, and optionally a body. And the server responds similarly with a response packet, a response line, some headers, an empty line, and optionally a body. And so when it comes to the conformance of these of the HTTP, it's defined by various RFCs which act as the standard and ground truth to how the protocol should function. For example, if the client decides to send a packet with 2 host header fields, the RFC will tell the server that if it receives this, that it should respond with a 400. And so if the server is conformant, then it will do just that and respond with a 400. However, the server is not always conformant, as exemplified by a previous study last year by Watson, Strauch, and Stock, who tested 106 rules from the RFCs and tested them across popular local and online web servers. What they found was that more than half the rules were violated at least once. And so going back to our example, assuming the server is non-conforming, then it's going to take this packet, it's going to accept it, and respond with the 200 status code. And this example gets more complicated when we consider that in reality, whenever the client sends a request packet, it more often than not doesn't go directly to the server, but crosses a middle box such as a proxy. So if there's a proxy in the middle, what it might do, as an example, is remove one of the host header fields in order to make the packet conformant, and as a result, the server responds with a 200. But because of this, it creates a black box scenario to the client, where to the client, 2 outcomes might happen based on whether or not the middle box decides to remove the host header field or not. And so it might receive a 200 or a 400.
And so this discrepancy in behavior is a result of the incompleteness of the RFC in specifying what exactly the middle box should do in this scenario. But why should we care about what the middle box does? Well, firstly, if the RFCs are not explicit in how the middle box should behave, then we end up leaving the decision to the implementers, which will result in varied middle box behaviors, especially in certain corner cases, which will lead to gray areas, which could lead to security gaps, such as request smuggling, where an attacker takes advantage of the inconsistency between an HTTP proxy and the origin server with their interpretation of content length and transfer encoding headers. Secondly, because of the presence of mailboxes, we're unable to pinpoint the origin of conformance issues in an HTTP processing chain. And so the study I brought up earlier highlights this, as they mentioned that their tests are inherently incomplete, as they don't consider the fact that intermediaries could be sitting between the client and servers and could generate or modify the packet, leading to the same black box scenario I mentioned earlier. And so how do we define conformance when it comes to mailboxes? The RFC requirements are sometimes ambiguous, which leads to issues in defining this properly. So to start, when requirements mention a server, it is unambiguous in this case because in RFC 9110, section 3.7, it states that the reverse proxy acts as an origin server. And so any requirement that specifies a server will also apply to the proxy. On the other hand, there's not a similar statement relating to requirements which specify the client. So what should the proxy do in these scenarios? This is one case of ambiguity. Third, when it mentions generate in RFC 9110, section 2.3, it states that the verb generate only applies to implementations that create the protocol element. And since the proxy's role is simply to forward and not to generate, then these scenarios shouldn't apply to them. However, what if the proxy is translating between HTTP 2 and HTTP 1, for example? Is this considered generation? And so should these scenarios apply to the proxy? This is another case of ambiguity. Finally, in some scenarios, it does mention a proxy explicitly. However, this is only mentioned a handful of times. And in other requirements, they specify two distinct behaviors between a server and a proxy for the same requirement, such as the presence of a white space between a field name and the colon. The server must reject it, but the proxy must remove the white space. And so this contradicts with the earlier statement that the proxy should behave as a server, because in this case, it's saying that it should behave differently. And so this is another case of inconsistencies in the RFCs. And so our contributions is that we want to show that some specifications are incomplete and lead to different interpretations and implementations. And they also create discrepancies between behaviors towards requests and responses for the same requirement. And finally, that isolating a single endpoint to measure conformance leads to inaccurate results. And so we took 47 requirements from the RFCs, so rules which include must and must not keywords, and we answered these two questions. When sending a non-conformant request, does the mailbox modify it or send it as is, or does it reject them? And similarly with the response, does it modify the non-conforming response, send it as is, or reject them? And so for our experimentation, we use the no pass around framework, which is a distributed framework designed for the detection and analysis of mailboxes. We defined three distinct behaviors for the proxies: unmodified, so forwarding them without modifying the packet; rejecting it, so sending a 400 or 500 status code; or modifying it such as to make it conformant and then forwarding it to the intended recipient. And so the mailboxes that we tested are these 7 local proxies and these 5 cloud proxies. For the local proxies, we used Ubuntu 22, and we use the default versions and configurations that are installed when using the APT package manager, as we care to test their out-of-the-box behavior without modifying anything else ourselves. So we want to put our shoes in the shoes of the implementers. And so the cloud proxies, however, they should be up to date with the latest version when testing with them. And so to summarize our results, this table shows the different behaviors across the proxies, and it shows that there are no consistent behaviors adopted by a proxy towards all the tests. And so all the proxies behave differently, and they have their own, let's say, fingerprint. And this is exemplified by the vectorized representation on the left, which shows all 12 proxies on the y-axis, and the tests on the x-axis. And you can see each one has its own distinct fingerprint or unique behaviors across the tests. And this is again shown by the Pearson correlation matrix on the right, which shows that no two proxies are alike except for Nginx and Azure, which could hint that Azure uses Nginx as the underlying system for the proxy, but we don't know. And so for the overall test behavior, we see that more than half the tests, non-conformant tests, were left unmodified, with a quarter being modified and rejected each. And of the 47 tests, 7 experienced unanimous behaviors across the 12 proxies, but the remaining 40 had non-unanimous behaviors across the proxies. So there was at least one proxy which was behaving differently. And so as an in-depth example for one of the tests and how we tested it, this RFC requirement says that an origin server with a clock must generate a date header field in all 200, 300, and 400 responses. And so we test this by sending from the server a response without a date header field, and we see what does the mailbox do. However, the issue with this specific requirement is that if there's no date header field present, then it could cause inconsistencies in the caching and logging mechanism of the receiving endpoint, which could lead to things like cache poisoning or harder incident response due to the lack of timestamping. And so we mentioned earlier that RFC 9110 states that the proxy should act as an origin server, and so it shouldn't forward it unmodified, as this would be considered non-conformant. But then also mentions generate, and so the proxy, since its role is to forward, it shouldn't apply to the proxy. And so here we have a contradiction. So in our test, we found that Cloudflare and Imperva leave all 3 categories of response codes unmodified. And the issue is, from this requirement, we cannot confidently say that these are conformant or not due to the ambiguity in its description. And you can see that when isolating this requirement to just the 200 responses and testing this, 5 of the proxies left them unmodified and 7 left them modified. And so why did some proxies opt to modify the response when their only role was to forward the message, apparently? So we don't know, we cannot say whether the unmodified ones are conformant or non-conformant, and similarly with the modified. And this is caused by the incompleteness in the RFC, which leads to the freedom of behavior of the implementation, which leads to this split behavior between the proxies. You could raise a point that these RFCs are fairly new, releasing in 2022. However, and so they don't give enough time for the proxies to implement them properly. However, a lot of these requirements are actually repeated requirements from older RFCs, such as this one from RFC 7231, which was released 11 years ago in 2014, which states that if it receives a packet without the date header field, then it must add the date header field itself. And Cloudflare and Imperva don't do that, so it's been around for 11 years, and so I would say they're considered non-conformant. And we believe that a lot of these issues arise from incompleteness, and this can be solved by, let's say, having a catch-all statement or umbrella statement, such as for HTTP2 in RFC 9113, which mentions that if an intermediary receives a malformed frame and it defines what a malformed frame is, it shouldn't forward it and should raise an error. And so using this, if there's a requirement that's ambiguous in how the behavior of the mailbox should be, then this would cover the behavior, and the implementers would know that regardless, it should raise an error. And spoiler alert, we are testing HTTP2 conformance, and this statement makes a huge difference when it comes to conformance of the proxies. And there are cases where the proxies behave differently towards requests and responses for the same requirement, such as this one, which states that the recipient of a carriage return, line feed, or null must reject the message or replace it with a space. For the request, all 12 proxies reject it successfully, but for the response, 7 of them decide to leave it unmodified and forward it as is, and 5 of them decide to modify it and replace it with a space, as mentioned in the in the requirement. And so to conclude, we showcase that the HTTP1 specifications are sometimes incomplete for proxy behavior, which lead to various interpretations, hence split implementations across the proxies. And it also has introduced discrepancies between the requests and the responses. And finally, us having control over both the client and the server allows us to pinpoint the message alterations in our tests and accurately test the conformance of the proxies. And thank you for listening. And if you have any questions, I would love to hear them.
Yeah, perfect. Thank you so much for joining us here. You already received some feedback from Mark Nottingham in advance on your paper, so I think that was very useful. Maybe you want to also reply on the HTTP mailing list to some of these things. Please feel free to engage there. I think one high-level point he was making is that it's not necessarily expected that all proxies behave the same, but I think it's still very interesting to understand when they behave differently, what the decision is behind that, if it's just kind of random, or if they have different goals, different motivations. So definitely interesting to look further into that. I don't see any questions in the room. Last chance to jump at the mic. I see people who try to jump at the mic. Just come to the mic. But it's fine.
Hi, Vaibhav
Say your
Bajpai.
name, please.
Vaibhav Bajpai, House of Platna Institute. Thanks for the talk. I still find it very useful. I'm a bit confused though. When you say proxy, do you mean these proxies are terminating the TLS connection underneath, or you are not looking at TLS at all? Or are you assuming these are HTTP connections which do not use TLS underneath, or what are we looking at?
For these requirements, we're only testing HTTP1, and so we're testing them without TLS. So just plain text HTTP1.
Okay, so follow-up question would be, do we have statistics on how much of the web is unencrypted, how much HTTP1 without TLS exists in practice? You motivated a bit in this first slide, but this was mostly talking about the share of HTTPS, so which doesn't concern your study.
Yeah, the statistic just mentions HTTP in general, so HTTP1, HTTP2, or and so on. But in our test, we only focus on HTTP1. I don't know the statistics related to how much of it is encrypted or unencrypted, but I mean, the RFC doesn't mention that it has to be encrypted, unlike HTTP2, which should be encrypted in flight. And so we just test without TLS.
Yeah, if I have this statistic roughly in my head, I think it's like still around 30% HD1 traffic, but I think most of the traffic is still encrypted, but probably that doesn't matter here.
Thanks, Mahmoud. And also, I think he's 4 hours west of us, so it's 7 in the morning. Thanks for the extra effort. I appreciate it.
Thank you.
Yeah, generally, thanks to all the speakers who joined us at uncomfortable time zones. But that's the end of our session. Hopefully we will have more in-person speakers at the next meeting, but otherwise I hope you still enjoyed this presentation. Thank you, everybody. And thanks to Gautam for the notes.
Good.